So I'm going to try and cover very, very lightly a whole bunch of stuff to do with sediment properties and water quality. I've listed a few names there who need to be acknowledged. Murray Hicks will be known to a lot of people. Sediment erosion area. Mention also the NIWA laboratory, especially Von Ovenden, who did a lot of those. I think he did pretty much all those analyses that Simon's just been about on the source soils, source erosion sources, and also on the river sediments I'm going to be talking about. So what I thought I'd cover, this is a bit of a piecemeal approach, the Manawatu River sediment sampling, which will link up to the erosion modelling. The issue of turbidity measurement is the second thing there. There's a poster over here about why I think turbidity is a very poor metric. Just mention why it is. Effects of fine sediment on rivers, the national policy statement, it's already been referred to, and it gives standards for fine sediment in the sense of visual clarity and also deposited fines. And I'm going to mention briefly downstream effects of fine sediment. Because, you have to have the source to the sea view of erosion, producing sediment that does damage all the way down through rivers to the sea. And that'll lead, I hope, to the next topic, which is modelling of river sediment dynamics as part of the broader test framework. So the Manawatu River work, the catchment there from the Lawa website showing Horizon's network sites. Adopted 3 of those sites. The Manawatu Teachers College was sort of no-brainer, key site in the Manawatu. The Pohangina tributary coming in from the north, and the Turamea, which has also been already talked about, the Turamea coming in from the south on the east side of the main divide. The Manawatu River being a rather strange river cutting through a main divide. At each of these sites, we had, or Horizons, had auto samplers that they were able to fire up for us to take samples over flood events, and they also ran continuous turbidity monitors, such as the SON shown here. The turbidity is that one, I think, the 6 sensors on the SON. And so we had high frequency turbidity, which we were calibrating to measures of sediment metrics, not just sediment concentration, but other metrics I'll explain in a moment, from the auto sampler. So what we were essentially doing was on flood events, the hydrograph of the flood event here shown in blue. We took samples, those are the brown spots. Suspended sediment concentrations were measured on the auto samples, and those were over the long term used to calibrate high frequency turbidity, which is the continuous line, wiggly, slightly wiggly. You can see most of the suspended sediment concentrations on this event is slightly higher than the long-term sort of calibration, and that's because sand content of the suspended sediment is variable. Sand can convey a lot of mass, but it hardly affects turbidity at all. What turbidity is a much better proxy for is the light beam attenuation already mentioned by Simon, and is this inverse correlate with visual clarity. So that's what we did on a range of events at both the main river site and the 2 key tributary sites. Here are the calibrations against turbidity. So these are plots of turbidity. On the left, we have suspended sediment concentration and its mud fraction, the 2 different lines there. The mud fraction, as you'd expect, much more closely related to turbidity. The label is falling off the graph somehow, but that's the turbidity range on a log scale there. So yes, the mud fraction correlates better with turbidity because mud includes the refined material that attenuates light, scatters light most effectively. Whereas some of that scatter in the sand in the suspended total suspended sediment concentration is due to the sand friction. Looking at the right-hand side there, we've got the calibrations of beam attenuation to turbidity for the three sites, Teachers College and its two tributaries, which you can see from the R-squared. So we're now talking much closer calibrations, much more precise to beam attenuation than to suspended sediment concentration. And just a bit of a teaser really to show some hot off the press work. We've looked at, we took the turbidity record at the Teachers College site here and turned that into visual clarity from our calibration to beam attenuation. That's the blue line. Compare that with the long-term measurement of visual clarity at that site, which has been done since 1989 by NIWA and then more recently by Horizons. And there's a bit of a discrepancy. I'm trying to figure out the reason for. Quite sure why we don't get quite a rather closer register. It may be simply that in the 2 years, 2020, 2021, when we were running the sampling of the Manawatu Teachers College and the other sites, we had a comparatively dry year. It may be simply that. We figured out quite why the discrepancy there. But we're in the ballpark anyway. So the median clarity at the median visual clarity at Teachers College in the vicinity of 1 metre. Okay, so that's the Manawatu work. And I've been talking a lot about calibrating turbidity. And why do we need to calibrate turbidity? Well, it's been known for a long time turbidity is not created equal. Different instruments and give you different numbers. One study came out quite recently showing a 5-fold range in turbidity of across different sensors. So people have come up with this standard, the ISO 7027 standard, which specifies near infrared light scattered at 90 degrees. And you'd expect that would give a closer register between different turbidity instruments. And indeed it does, but they're still not exactly the same. This is data for the the Mataura River, where NIWA had 3 different ISO 7027 compliant sensors running. Here they are here, color-coded, and color codes consistent with the plots, and you can see the turbidity on the different instruments. It's running parallel, but it's not the same, about a 2-fold range. So this is a bit of a worry when you think about it, for a variety of reasons. So we got some Envirolink funding to look at why, and did some tank tests. You can see the tank there on the left with river silt in it, and in the middle photograph, kaolinite has been added. Kaolinite clay has been added as a slurry to the tank. We also looked at pond algae, and in these 3 different media, 3 different, very different kinds of sediment, if you like, we ran our 6 ISO 7027 compliant turbidity sensors parallel, and they don't agree very well. This is just one example. This is for river silt. You can read more about that in the poster there. A rather similar situation for kaolinite, for example, but different order. So there's no way to take one turbidity sensor and convert it to another. Your turbidity is not going to agree with some other guy's turbidity over the hill. They're just different animals. It's just a fact of turbidity being what it is, which is a completely arbitrary measure linked to the scattering of this artificial substance called formosum. So the ramifications of it are actually quite far-reaching. We should avoid reporting, we argued, in FNUs and NTUs and so on. There's no need, therefore, for formosum. That's a real surprise to a whole lot of regional councils who have been busy measuring turbidity since the year gone. I'd say high-frequency turbidimeters are useful beasts. They'll remain very useful in erosion sediment work, but they need to be calibrated to light beam attenuation. And we do that with this little simple setup in the laboratory, which we're now doing routinely. In the future, I imagine some of the other environmental consulting labs will also run that off of that service. And perhaps more widely, don't use turbidity in studies of sediment effects on aquatic biota or environmental standards, which brings us to environmental standards and what the effects of sediment are on river biota and downstream. We published that in hydrological processes. So what are the effects of fine sediment? We've done some work, Murray Hicks and I, since about 2015 for the Ministry for Environment towards the idea of having sediment-related standards, which became by some crazy system, came up with a different name. They got the term environmental attributes. So what we ended up with was promulgating attributes for, sorry, I'll just back up there if I can. For visual clarity, as we've already heard, but also deposited fine sediment. And those tables referenced there are in the National Policy Statement. No standards for turbidity. We've just done this set of laboratory tank experiments I mentioned in time to say having standards for turbidity would be a very bad idea. And that was agreed to by the steering committee for the Ministry for Environment had set up. More recently, a document has come out giving guidance for how to implement these standards in the National Policy Statement. And Marlon, you'll be hearing from shortly, was the lead author of this report here. I'd commend your reading on how to relate things like sediment loads to those standards. Now, so far I've been talking about, I'm going to have to speed up, just about effects on rivers, but sediment also affects downstream. And so NIWA's done quite a lot of work on muddy plumes and what their effects are. And this is Wellington Harbour, almost filled up with a great big muddy plume coming in from the river up here and then moving southwards. And so the question is how to study this kind of thing, and we can remote sense it if we're lucky enough to catch them, but that are very transient. They only sit around for a few days, so usually the satellite radiometers that we would be using don't miss them. So we came up with this gizmo here, which is a sonde and a suitcase. Essentially, there's the suitcase, and the sonde is the green sleeve on it, with a bunch of complicated plumbing, bringing water in from into the boat as it screams along on the plane. And the schematic on the right shows how that works. Basically, we have to get rid of the bubbles in the water that produce the white there. And that's done by this thing called a vortex debubbler, which spins the water around. The air comes out the top, and then the conditioned water is measured on the flow cell of a standard sonde. And periodically, you can take a water sample to calibrate the sonde sensors. So we did that. This is Wellington Harbour again, and another flood in the Hutt River, and very high turbidity coming in the river jet, and that's what it looks like. The sonde about to do depth profile, and the ambient harbour water is sort of around 3 FNUs nominally, and the plume is outlined by the zigzag pattern of the boat pumping water to the sonde. So what are the effects on sediment down in the sea? Seagrass seem to really dislike mud. And New Zealand has historically lost some of its seagrass bed, which are really important for a whole variety of reasons because of mud. The working hypothesis was that the mud prevented or cut down the penetration of light and therefore cut down the photosynthesis of this high light plant. But that didn't seem to be enough on itself. There's something else going on. We had a PhD student from Spain with animal seagrass who looked at this and tortured 4 little seagrass sprigs in the lab by taking the light down very low. That didn't hurt them too much. Then putting mud in the tanks, that didn't hurt them. But if they put mud in the tanks with low light, suddenly it knocked out seagrass. They don't like mud because mud both reduces their light and reduces their oxygen supply to their roots. They need to have light to photosynthesize and pump oxygen to their roots, which would otherwise go anaerobic. And that was laid out on this little model here. I'll back up again. I'll do this time. And we published that review, which I'd commend to you as something that you might want to think about citing if you want to sort of show how learned you are about the far field effects of trying to justify some work on erosion, perhaps. If you could say, show you know about what this stuff does to seagrass, that might be very impressive to your funders, to the reviewers. Good suggestion. We're going to hear in a moment about modelling, including modelling of sediment dynamics. But we did have some work with a postdoc at MIWA. Some of you have met Jen Drummond from Spain, more lately of Birmingham University, who came up with this stochastic modelling approach to find sediment-feeding bacteria, which are really, really fine and really, really light sediment and would never settle. So you can't sort of have them modelled as a simple settling process. The way they're taken out on the left there in the base flow condition is the river water is exchanging by hypereic flow, the hypereic zone, which is that surface coarse bed sediment. And some of those particles go into the hypereic zone and they get stuck there. And then they load up the hypereic zone under base flow conditions. And then once you get a flood come along, that sediment store can be remobilized. The water very rapidly goes very turbid and the particles are flushed downstream. So that might be another approach, especially important in the area of particles, the size range of particles around 1 micron roughly, that are most important to visual clarity. And I think that's it. That's the article that we published on the stochastic modelling approach. As I say, it was targeted at microbes, but it worked also very well for turbidity as a kind of a proxy for very fine inorganic sediment. Take homes, sediment properties, I would say, are as important as sediment mass concentration and mass loads, and light attenuation is as important as sedimentation as a damage to the water system. Second point there, the national policy statement requires management of visual clarity as well as fines deposition. But we have to consider also the damages to downstream and coastal. And that includes seagrasses. Our review of sediment effects on seagrasses with this new understanding of the mechanism of effect, I think can be used to justify erosion control to avoid far field damages. Turbidity, a useful high frequency proxy in erosion sediment management. I'm sure that will stay the case, but it needs to be calibrated to beam attenuation. And we can dispense formicide, which is a nice thing to do because formicides are really nasty, doesn't let you anything. Thank you.